So this is really excellent. This intimate space, this number of guys hanging out, we'll be able to keep this very collaborative because I want you to walk away from this session really with some knowledge that can begin to answer curiosities or begin to assist you in moving in the direction that you may be compelled to look at, whether you're already involved in the concrete industry, the tilt-up industry, or a related industry, or just thinking about what is happening all around you. That's what I'm here to present to you today. So good morning to each of you. As Len said, I'm the technical director for the Tilt-Up Concrete Association. My jobs are quite varied. I do a lot of speaking engagements around the world. I was just in Mexico a couple of weeks ago, working through a simulcast translator to really educate the Mexicans on bringing tilt-up beyond the box thinking and working into the modern areas where we see tilt-up excelling. Today I get the chance to talk a little bit more about a specialty of mine that I've been working on since the early 90s, and that's the thermal performance of tilt-up. But you really can't talk about the thermal behavior of tilt-up construction without looking at its influence specifically on the architectural market, because the two work hand in hand. We can build boxes. We can build gray boxes, and we can insulate those gray boxes, and we can prove the energy efficiency of a gray box. But that's not very inspiring to the market. And so what we want to do is understand the energy code that is in place today, kind of where its background comes from. Let me catch up with my slides here. There we go. So I'm going to talk about the modern tilt-up movement and what's taking place, because it is a direct response to, in many ways, the energy codes that are out there. We're also going to talk about the history of codes just a little bit. We can get too deep into energy code development and energy performance, and none of us will make it out of here without coffee. So we won't go too deep into that. But we are then going to also then take a look at the primary elements of the energy code that influence tilt-up construction and allow us to move through the modern aesthetics and the modern delivery methods that we have today. And then hopefully through that, be able to create a conversation, whether that takes place here in this room during the presentation, which I always encourage, by the way. If you have a question that comes up on a slide, put up your hand, shout it out, whatever you have to do. We can take this really casually. But also then what happens after today, and where do we go from here in the conversation about modern concrete technology, energy performance of it as a principal solution to what is being required in today's marketplace. So with that, what I want to establish first is the unified understanding that concrete is the absolute best building material and building system on the planet. Now, if that were not the case, we would not still be building with concrete technology that has its roots back centuries and centuries and millenniums from now. So concrete's the only building method, the only building material that still exists from the time that it was really first put in place. You look back circa 600, 800 AD, when the Romans were putting concrete aqueducts in place. There's still the argument, were the pyramids concrete, were they masonry? So regardless, concrete is an age-old tested material. We know that the durability stands there. Not to mention the fact on the screen are some of the most awe-inspiring architectural works done in what? Concrete. So concrete has that ability to answer the call to high-end aesthetics, to high-end iconic structures, and a way of inspiring not only the present generation but also future generations to see how true and how perfect concrete can be. So we take that as our start, and we realize that what we're really talking about is sustainability. Now there's a 50-cent word that has become a $1 million word in today's marketplace, where sustainability is the characteristic that everyone is talking about, everybody desires. Architects look first at how can I make this project sustainable, because clients are coming to them saying, hey, you know, we really want to do justice to the money that we're going to spend for this project. And we want to do it with sustainability. And so therefore we have to understand what can influence the sustainable future of building design and construction. And tilt-up certainly answers that call. We look at structures that are 50 years old, 60 years old, 70 years old now in tilt-up, and look very much in many ways the way they did the day that they were put up save for maybe the quality of the paint or replacing some of the caulking systems that secure the panels weather tight between the two of them. Versus other systems in the marketplace that when we look at a couple of decades down the road, the dilapidation that happens with structures, even to the fact that there's short-term investments that are planned to be removed. So the materials, whether they're recyclable or not, the energy that was put into building them is completely lost. And so that's part of the characteristics that make tilt-up and make concrete in general, but tilt-up in specific, the system for modern development that we're really characterizing as the most sustainable, not just the most energy efficient. So as we look at tilt-up construction, what I want to focus on in terms of its modern applications is that tilt-up really has two different languages. In terms of architectural style, tilt-up buildings will do one of two things. They will replicate an existing historical, maybe a regional characteristic that will fit into an environment in some way, shape, or form, much like this project that you see here, this chapel, where they've brought in stone along with the tilt-up structure to emulate the historic cathedrals of the past. Now, it also has a very modern style to it, but in many ways it also recharacterizes history. We do that also in the way that the panels are textured, not just painted, but textured and incorporating historic materials. In this case, down in Charleston, South Carolina, bringing in the brick characteristic of the historic culture down there. It's an aesthetic that is required out of whatever building type is built. And then when we combine it with the tilt-up delivery system, we add the energy efficiency to it, as we'll begin to talk about through the rest of this presentation. But being able to emulate the historic culture is one of the bigger aspects of tilt-up that has engaged the modern use of the building system. Again, beyond the box thinking, capitalizing on its energy efficiency as well. There's also the uniqueness of tilt-up, and this is to create structures, again, an idea of iconic delivery, iconic structure development, architectural aesthetics, and tilt-up to be its own style, because it can do things in many ways that any other building system cannot create. At least it cannot create it very energy efficiently or cost effectively. And so tilt-up style takes us into a new genre of building types, really characteristic of what history has served as we look back at structures, again, like the Roman aqueducts that I mentioned previously. When we look at tilt-up construction, we're looking at a library of benefits to the project. We're here to talk about its solution from an energy efficiency perspective, because the modern energy codes are very challenging to today's design teams. However, the system being able to provide the combination of aesthetics, to do it at reasonable value, and I use the term reasonable value because you can take the cost of building construction in either direction. You can build as economically as you choose to build. You can build as lavishly as you choose to build, and one building system can deliver that entire framework. Schedule and early occupancy, the speed of construction is also very integral to both sustainability in terms of its energy use, the amount of energy taken to build a building, but also because it gets projects moving that much quicker towards occupancy, much more quickly towards the high-end use of the structure. Durability, sustainability, safety, versatility, these are words that are all attached to primarily the use of concrete, but because of the delivery system itself, the ability to move beyond current or trusted delivery systems for concrete, cast-in-place concrete, for instance, to be able to do all of this on the ground and to put the structures in place very quickly, very safely. But again, energy efficiency and talking about air barrier effectiveness specifically as we engage the tilt-up industry in today's presentation are what my goals are. High-end aesthetics, I've showed you just a couple real quickly, but as we move through the genre of tilt-up construction and we look at why tilt-up today, And why does it engage energy efficiency? I said earlier, framed this earlier, that we have to keep in mind it's the aesthetics. Because it's very much the aesthetics of tilt-up construction that leads to its energy efficiency, its superior energy efficiency. It's very much the aesthetics of tilt-up construction that has us in this room talking about why is it a primary solution for today's marketplace. So whether we're talking about small projects like this chapel, where you can see very intricate panels that interlock, that frame windows in different ways, that present a natural concrete finish, that has the ability to deliver durability and longevity to a finish without excessive maintenance. These are characteristics that really challenge building systems in general and lead to tilt-up solutions being a primary opportunity. We also talk about the entry of the system into multi-story. Again, when we think about why do we build the way that we build, oftentimes we segment a market or a construction system to a specific market because it's the way that it's always been done. And one of the aspects of tilt-up as a principal energy solution is its ability to grow into all building types and a much broader cross-section of the marketplace. Now, maybe not high-rise construction, but the systemology that's used in tilt-up construction has been applied to buildings as tall as 22 stories. It's a modification of precast and tilt-up, but it's the delivery system that gets you to that point. The idea of how do you interconnect and how do you create envelope, enclose space, and do so energy efficiently. But the fact that today's tilt-up market, it has a significant number of three-story to six-story structures, make it characteristically a great solution for a much larger cross-section of the marketplace, particularly when we're talking about what is the modern movement of today's office building, where's the modern movement of today's multifamily structures, or the residential structures that we see being built here in Toronto now. Granted, some of them are 30 stories tall, and that makes it a much different conversation. But in a lot of the North American market, we see structures in this 3 to 6 story range moving out into the suburban areas and really multiplying, maximizing its space on the built environment. Form and shape is another characteristic that brings tilt-up to a modern dialogue that is very eminent in its exceptional delivery both of energy solutions but also architectural solutions. The fact that we're dealing with modular panels that can be segmented, that can be connected at angles, can be left at angles, can be curved. These are things that take it beyond this idea of box delivery, which really enters into a reason why we're talking about it as an energy efficient solution. I go back to my first statement. If we're just dealing with boxes, gray boxes, warehouses, if we just put that out there as the idea that maybe each of you have in your mind as the right building type for tilt-up, beyond that concept of where tilt-up is applied exists everything else that is in the built environment. And so being able to engage it from an architectural solution is paramount in moving forward this idea that we can capture the extreme energy efficiency of a building system and apply it to our entire vernacular of building design and construction. And that's really what I want to bring to this table today, is the combination of its architectural solutions with its extreme performance. And so things like angled panels, whether they're panels that are angled out of plane, angled in plane, maybe the edges of the panel are angled, but these are characteristics that you see throughout the tilt-up industry as we look across its market. But then also extreme shape development. When we're dealing with a system, and I'll show you some construction photos in a little bit so you can see how we get from point A to point B, but in this case we're looking at a very dramatic shape. Now, how do we build that shape? What do we need that shape for? But if we're trying to challenge ourselves, in this case, to have this archway, this masonry archway, it is almost an impossible design that has been put forward until we reconcept what it means to build, and we build these shapes flat and tilt them into place. and that is the excellence of the system to give the contractor the power to change the dynamic way that projects are built, and to look at ways to characterize the architect's vision through the built form. And so we take these interlocking panels to a new level, and you can see some houses presented here in front of you, some smaller panels for houses. But the characteristics of offset joints that in this case are opened up so the glass can exist between them. So we can bring in light in different ways, whether it's light for the sake of creating vision to the exterior, or maybe it's just light for the sake of bringing in ambiance and creating spatial characteristics that would otherwise be required out of natural or out of artificial light. So there is another aspect of bringing in energy solutions by lowering the requirements for artificial lighting controls versus bringing in more daylight. Tilt-up also has the ability to do this in combination with many other aspects of the building environment. And in this case, we're integrating some steel, some storefront technologies along with the concrete. This is a row home development in San Diego that really kind of evidences the ability of tilt-up to play in the landscape of urban density, but also do so with very natural characteristics, maintenance-free performance. The idea behind tilt-up, again, is the panels cast on the job site, lifted with cranes, some of these becoming massive panels. And you can see here from the size of this particular 4-story panel that's being erected, the size of not just the panel itself, but the openings that are framed within the confine of the panel. Stand these panels up next to each other, and you can see just the tremendous amount of glazing system that's an opportunity for the project. Now, we're also going to talk about minimizing glazing as we get into energy code, the understanding of the energy codes. But that doesn't mean that it can't be done. And I will challenge that in so doing, as an energy efficient envelope, integrating insulation technology along with its the thermal mass characteristics of concrete, allow this system to maximize its glazing and keep that glazing system energy efficient along with the building envelope. So we do have that that opportunity to maximize it. So there's just a little bit about the modern characteristics of the market. I wanted to kind of wet your whistle with really some projects that you can look at and say, wait, I didn't think that was tilt-up. Or I don't think of that type of a project when tilt-up enters my conversation. Are there any projects up there that surprise you? Not you guys over here. Yeah, okay. All right, so hopefully that just kind of sets the stage now for looking at it from a different perspective, and that's from the energy codes. Now, I will tell you that tilt-up and precast systems, tilt-up itself simplifies the energy code. How many of you believe that the energy code is a really problematic or complex code? It's complex, right? You think it's complex? Complex? Okay, I will tell you that in concrete, in insulated concrete, in tilt-up insulated concrete, the energy code becomes a very easy system to navigate. There are really 3 characteristics of the energy code that we focus on or that we talk about. And so I want to first give you an idea about the energy code itself and why have we gotten to the point where we are. Because it really is, it is of great interest to me how quickly the energy code has amplified, exponentially added requirements to building systems in the last 10 years. Really, in the last 10 years, we have seen more growth or more conservatism, let's say that, right? More conservatism in the energy code than at any other period in the history of construction. In the last 10 years, you've been asked to create buildings that are tighter than at any other point in the history of modern design and construction. Now, first of all, I'll iterate that the energy code is not there to prevent you from building with a system. You can still go out and build with stick technology. You can still go out and build with metal buildings. You can still go out and build with masonry. You can still go out and build with tilt-up, with precast, with straw bales, with adobe. You can build with anything, really. The energy code does not prevent a system from being used. What it does, though, is it really complicates the steps that you have to take as an architect, as an engineer, as a contractor to achieve the energy efficient requirements that are now in place. And so this is why we talk about tilt-up as a principal energy solution, is because of the simplified process that you must endure or that you can prove with this building system, whether it's applied to, again, a warehouse or a single family house or something much larger. Now, I'm from the United States, and so a lot of my base for energy performance comes from the IECC, the International Energy Conservation Code. It is an international code. It's developed by the ICC, the International Code Council. Canada, as you know, has a national code. It's now the national, National Energy Code of Canada for buildings. Both of them come from the same foundation. They both look to ASHRAE 90.1, which was a document that was first developed in 1989, and it is the one that really is instrumental in changing the idea of what energy efficiency is for building envelopes. It's the first time that the conversation about thermal mass came into our dialogue. It's the first time that really stringent constraints were put in place for how does energy transfer through a wall and how do we calculate that energy transferring through the wall. It's the first time that energy codes created prescriptive requirements and at the same time allowed an alternate compliance path so that you could model the thermal behavior of a building and prove it from an energy code perspective and build in that way. And so at the same time that it creates much more constraint on how we design and ultimately how we build, it also liberated the dialogue that can happen between the contractor and the architect and the engineer and the mechanical engineer to create the right solution for the project if you understand the componentry that's being used. And so just those slides kind of show you the development of the US-based IECC on the left. Now, in the US, the big crunch was between 2006 and 2009 because the federal government said, hey, in 2006, the energy code is well designed, but it doesn't go far enough. We're still using way too much energy. And so the federal government said by 2009, we want the energy code to decrease projected energy consumption by 30%. And so the most brilliant minds in the energy code development got together and worked hard on trying to figure out how do we reduce intended or developed energy consumption by 30%. They couldn't do it because it's a very tough task, not only to implement those types of controls, but then also to politically move it to acceptance. They were able to achieve a 15% reduction. Similar things happened in Canada as you moved from the Model National Energy Code for Buildings, MNECB of 97, and you pulled together, you saw this collaborative be pulled together, and in 2000, it took all the way to 2011 to the delivery of the NECB that finally got to the same point that we saw in the IECC in 2009 and 2012. So 2012 is when the IECC finally delivered a 30% reduction from the characteristics of building design that took place in 2006. So it's a long time. Now, keep in mind that code generation happens in 3-year cycles generally. And so it really isn't that long of a time. I'm the past chair of the Concrete Committee for Residential Construction, and the amount of time that exists between a 3-year cycle from when you're finished with a document to where you're finished with the next document happens in a split second at times. It takes that long to negotiate. It takes that long to figure out what's right, what's wrong, what's too much, what kind of bite-sized chunks can we take. In this case, the energy code, though, that we have in 2015 in the IECC in the US and in many international markets, and the 2015 NECB are almost identical codes. They're all based off of ASHRAE 90.1 2013. They all kind of talk about the same things. So I'm going to focus on some slides here just because we're here on NECB. The three elements that matter the most. Now we can talk about internal light density and expected outlet performance and characteristics of the HVAC system and radiant technology and all of the different aspects of energy consumption in the building. But we're here about a building envelope. And the reality is that tilt-up or any other building envelope can impact three areas of the energy code. It can impact the thermal performance, it can impact the air barrier, and it can impact the maximum glazing. Those are the three areas of the energy code that have been strengthened from 2006 to 2015. Now, how many of you have a Yeti cooler? Anybody have a Yeti cooler? That's like the rage. Everybody has a Yeti coolers. Not me and not any of you in this room. Okay, so a Yeti cooler. How many of you have an Igloo cooler? Yeah? You got an Igloo cooler. Okay, so the Yeti cooler is 10 times the thermal performance of an Igloo cooler. Now, I grew up on the Igloo cooler. You know, my mom and dad had it on the back of the boat. It had the adult drinks in it and the ice, and you know, they had the very weak metal clasp on it, and it looked like it needed to be thrown away 3 years after they bought it, and we still had it, you know, 20 years later. The Yeti cooler is sophisticated. It's highly thermal in its envelope. The way that the lid sits onto the base of the cooler has an interlock behavior to it, so that it doesn't let energy out through the joints. And ice will last in a Yeti cooler like till my kids are grown. So whereas in an Igloo cooler, you know, you replace it after a couple of hours. It's that kind of level of sophistication that is intended to be thought about in the building envelope. So when we go forward and we talk about why those three characteristics come together, it's really this. You can, in some way, the Yeti cooler, while it's superior in its performance, where do you go from there? You can only put so much insulation around a space, and then energy doesn't move through that. You use more energy to condition the energy that's generated inside the space than you do adapting to the energy that moves through the envelope that contains the space, if that makes any sense. So the idea behind the energy code is you must bring those three areas together, because the sum of the parts really is what they're saying. The sum of the parts and the way that you build the envelope are greater than the idea of the conceptual whole. It's a cliche, it's a statement that we use in many parts of society, but from a building envelope, it's the most characteristic statement that we can make. The sum of the parts is greater than the whole. And so we look through how the energy codes frame that. Now this extremely complex diagram is given to you in the NECB. And what it really says is, we'll simplify it. So here's whether it's NECB or 2011 or 2015. But here at the top is where we start, and you get to decide, do you want to do the performance path? Now, I do not know very many architects and even fewer mechanical engineers that want to do performance path on building design. Why? Because it's like doing iterative design in engineering. Nobody wants to do iterative design in engineering, so we gave it to the computers and said, you go figure it out. Because the more times you touch a project, the less economical it is. The more money you spend as a firm to design a building envelope, the less time you have to implement some of the things that the owner is really paying you for, such as the aesthetics, or the spatial solutions, or the detail level of the project. But in the case of solving an energy code, your first option is, do we want to do a performance path, or do we just want to go to our shopping market and just pull off things that work, and again, bring together the sum of the parts? And so if we say no, we don't want to do performance path, then we have this entire structure of looking at the energy code. It gives you prescriptive requirements for glazing systems, for the amount of insulation in the roof, for the amount of insulation in the walls, for the insulation under the slab, for the insulation around the footings, for the insulation around the pipes, for the types of mechanical systems that have to be used. And each one of those characteristics can be pulled off of the shelf, can be looked up, can be asked of a manufacturer and say, can you meet this, can you meet this, can you meet this, can you meet this? And if you pull together all those prescriptive requirements, right here, select code part 7, prescriptive compliance, and you're done. So we can very quickly move through the energy code and say, okay, we're just going to build a building where every component matches its prescriptive minimum, and we're done. But in reality, that might build a very expensive building. Because the characteristic of the building that we want to build may use something that exceeds that prescriptive minimum just by the nature of the product itself, which is where we are with tilt-up construction. Tilt-up construction is so more efficient, has such a high level of thermal efficiency capable to it, and actually inherent with the product, that it exceeds the prescriptive minimums multiple times. And so the energy code then allows you to look at trade-offs and say, well, okay, if we want, the old adage used to be, why would you insulate the walls? Let's just put 6 inches of insulation in the roof. So we'll just super insulate the top, not put any insulation around the walls, and the trade-off should be good. The net loss is less than the net gain. The net loss through the roof is less than the net gain through the walls. Well, so in the energy codes, there are caps to what you're permitted to do in terms of trade-offs, and so you don't see that level of design done anymore. So now we're looking at true minimum level performance for any individual characteristic, but as you increase the characteristic of one element, you're able to do trade-off calculations and still prove compliance, and then you can stop. But at no point in the energy codes can you choose can you choose to do the performance path and do some trade-offs in the midst of the performance path. Once you do a performance calculation, you stay within the performance path, because really that's doing the trade-offs at a different level. You're now looking at every aspect of the project and bringing it together. It's air infiltration capacity, it's glazing, the amount of internal energy that we generate. All of those things are being brought together. In essence, this is a more simplified model that I think makes sense to me, is that you can look at the prescriptive method, you can look at the simple trade-off method, or you can combine the two and you're going to meet your new National Energy Code. Or you can put together a team that understands thermal performance of the model itself, use an energy solution software to model the building, and you can prove that it meets the NECB. So those are the kind of the process that's being used. Well, why is that important? Well, it's this. Our building envelopes are quite complex, right? We don't build simple boxes. We stated that earlier. If we were just about the simple box, this presentation would have been over in 15 minutes. Because I can design a tilt-up Yeti cooler that will never need exterior energy put into it, but none of us are going to be happy, right? Nobody wants to be in that building. But if we look at, so this is a tilt-up building, a 3-story office complex, but when we look at the complicated elements of any building envelope, whether it's tilt-up or not, and we start looking at these prescriptive minimums, the roof, the wall, continuous air barrier requirements, maximum fenestration, these are the areas that when we look at each of those requirements individually become so complex that it really can constrain or confine the success of the project based on the system that we select. Minimum air leakage values through windows and doors and how they're integrated to the walls. All of these are requirements by the energy code. And in a tilt-up panel, what we're really talking about is a sophisticated system of structure, of continuous insulation, and of cladding. That's one panel. One panel in its monolithic thickness gives you structure, gives you continuous insulation, gives you cladding. Now, what do we do on this cladding? In this case, I'm showing you the historic replication, the thin brick technology that's integrated with the panels. But what do you see when you look at that cross-section? What do you see? Do you see any holes through it? You see any soft points? You see any moisture migration concerns? Now, one of the things that you don't see in comparison to other systems is you don't see air spaces. There's no airspace in there. It's a benefit for two reasons. One, there's no thermal cycling that takes place within an airspace that can lead to lower energy performance. But there's also no place for moisture to accumulate because there's no moisture to accumulate. Right? In essence, you have a monolithic concrete shell in its exterior condition here that moisture does not go through. There's a requirement in the NECB for rain screen technology when you're using any kind of a framed system or masonry system. You have to create a rain screen. In other words, you've got to have a barrier here that definitively stops the transfer of moisture. Not vapor, not moisture in the terms of vapor, but driven moisture, air-driven, wind-driven, liquid moisture through this cladding system. Well, this cladding system is high-strength monolithic concrete, and so there is no moisture penetration through that. There's a study that's done, I think it's by the Portland Cement Association, that shows that it takes 7 years for moisture, for water, to make it through 6 inches of concrete. If you just let water sit on 6 inches of concrete, it takes 7 years for water to transfer through 6 inches of concrete. So, in this case, we don't have 7 years of constant application of water to this condition, but we also have an integrated thermal barrier that is a water retarder. Water barrier is a new classification in the energy codes, and to meet the category of a water barrier or a vapor barrier, it has to meet a minimum perm rating. In this case, the extruded insulations that are in the marketplace are exceptional in their control of water vapor and are classified as a water retarder. And so this barrier then adds to the level of durability and the security that is created from air movement and water movement perspective, and at the same time creates the thermal barrier. It's continuous. You're looking at not a cross section. We didn't cut through a panel for this. This is the edge of a panel. This is ready for the next panel to be stood up next to it. So we have insulation that comes all the way to the edge of that panel. That insulation goes all the way to the top of the panel. That insulation goes all the way to the bottom of that panel. There is no point in that panel where insulation does not separate the interior layer of concrete, which is structural, from the exterior layer of concrete, which is architectural. And so there is the first answer to the building envelope requirements. Now, I could dive into the tables for you, and in Canada, just like in the United States, everything's based on heating degree days. The more heating degree days you have, the more insulation you're required to have. Now, in the latest IECC, the 2015 Energy Code that the U.S. is in the process of adopting, again, once you create a code, it takes a long time to adopt it. There are now insulation requirements all the way down into Florida, with the exception of the extreme southern tip of Florida. So every building in the United States from this point forward has to have some level of insulation in it. No longer can we just build concrete shells. What we're doing, though, is in addition, when we get into performance path compliance, the tilt-up systems have this structural layer of concrete on the back side. 6 inches maybe is the minimum, maybe 5-inch minimum. I've seen as thick as 14 inches of a structural width. Let's say, well, the tallest panel on record right now is 109 feet 7 inches tall for a tilt-up panel. That's a big panel. That 109-foot panel, I think, has either a 14 or a 16-inch structural layer. And so you've got that much concrete. There's an extreme amount of thermal mass that is evaluated in the building performance model. So as a design team, choosing to do the trade-offs and the prescriptive minimums ignores the fact that there's an extreme amount of thermal storage capacity that is insulated, that is just waiting to absorb energy in the building and hold it until that energy is needed to condition the building in the opposite direction. So in terms of its mass, the massive envelope, here's the other characteristic of energy codes is that you will see in the building envelope tables that if you're building with frame technology, you need, let's say, a common feature might be R19 plus 3.5. And so what R19 means is I can have R19 bats in the middle of my stick construction, but at some point I've got to have a continuous layer of 3.5, an R value of 3.5. Or they'll show you a layer for mass building envelopes, and it'll say just one number, an R10, an R15, something like that. That's because of the mass performance lowers the amount of insulation that's required to effectively condition and control the building envelope. So in the case of the energy codes, in order to meet a mass wall, you only need a mass of 35 pounds per square foot. That essentially is 2.8 inches of concrete. Well, in most sandwich panels, in most tilt-up sandwich panels, there's 2.8 inches of concrete just in the architectural width. The structural width oftentimes has 87.5 inches, or excuse me, 87.5 pounds per square foot of mass. And so what that really means is that there's this tremendously greater level of thermal performance, thermal mass that's capable if we go into performance path analysis for building envelopes. So let's take a look at insulating panels here. And I'm going to check my time. Oh, good. We've got 20 minutes. So I'll leave you 5 minutes of questions, maybe. Are there any questions to this point? No? Yeah, go ahead. How do you hold the two layers together? Excellent question. All right, so I'm going to show you some construction shots of that. So here you've got a slide that shows you 3 ways of insulating a tilt-up building. Right? So I've showed you a cross-section of a sandwich panel, which is the predominant way that tilt-up buildings and precast buildings are insulated, is the sandwich panel. Continuous layer of insulation, exterior face, and we're going to get to how do you connect those two in just a minute. The original way was obviously we erect a tilt-up panel, and if the client wants insulation, let the client come back and put insulation in there. And so they would oftentimes choose these interior fit methods where you have PVC channels and you've got rigid boards and they adhere them or mechanically fasten them, and that gives you insulation on the inside. But now you got to cover that with something, whether it's for fire code or for maintenance of the insulation systems for physical abuse, whatever or just cleanliness of the interior. But what that also does is it eliminates the concrete from the interior of the building. And I don't know about you, but I absolutely love concrete. And I want concrete to be that surface on the inside of my structure. So you could insulate on the outside. And we're all familiar with the EFIS systems. And EFIS systems have really given many constructions poor performance and bad names, particularly in frame construction, because the EFIS system is a very poor performance and susceptible to large deterioration over time because of the amount of moisture that can flow through those systems. And so that's really one of the principal rain screen requirements, which you would have it here in a monolithic wall. But insulating tilt-up panels in the past have also been characterized as problematic because of the way that they were, the way that they've been built. Now I'm showing a couple of precast panels here from 1980 technology, where you see large chunks of insulation that have been removed. And so when we aren't able to maintain continuity of the insulation, which is the stipulation in the current energy codes, your insulation has to be continuous. That means there is no point in the building envelope where insulation can be stopped. There is all the way out to the windows. The windows is a different rating system, so I have to take my insulation all the way to the windows. I can't stop. It would be much the same as in the United States, OSHA is our employer law safety protection organization, and they'll let's say fall protection. So right next door to the Hyatt where I'm at, they're building an office building, and there's the wood railing that's giving them fall protection up on the 12th floor as they're casting their floor. Well, maybe there's a structural reason why in the development process I really can't afford to have that railing there. And OSHA would say, There is no point where it's acceptable to not have fall protection. You've got to always provide fall protection. Well, that's kind of the same thing with the energy codes. The energy code is saying there is no reason why we're going to allow you to eliminate insulation because it's better for your construction, or because it's easier, because it's more economical, or because you just simply can't figure a way to design continuous insulation. You've got to have continuous insulation. And so we look at a tilt-up process now, this is this is actually a crazy project, regardless of what I'm going to use it from a site perspective, but this is showing you panels cast out on the job site. This is a 7-story dormitory, and the building's taking place all around the courtyard, so they're using the interior courtyard to cast the panels. But look at the height of those panels. I mean, those are 75, 80-foot tall panels all cast out there. But when we start tilt-up construction, here you've got the slab, you've got the face already poured, and the insulation back on the back side here in this lower section. Actually, this is an upper section of a wall that's this is a warehouse on one side and office on the other side, so that's why it's uninsulated below and insulated above. But this is one of the insulation systems that are out there. I think there are now 6 different insulation systems on the market that allow a contractor to do insulated panel technology. Most of them will have some type of a connector that penetrates through the insulation into the wet concrete, and as that concrete hydrates and cures, it grabs a hold of those connector ends, and then when the panel is lifted, those connectors are charged with the responsibility of picking up that face, and then they hold it for the longevity of the panel. Now, these are highly sophisticated systems. The other technology that's out would be a connector that fits between the boards. Does the same thing. You just space the boards based on what is the spacing characteristic of the connector requirements. And so you'll either have connectors through the boards or connectors between the boards that will hold those 2 layers together. Those are all non-conductive, and they're not metal. They're all what would be considered fiberglass or fiber composite, a combination of some type of a fiber, whether it's a carbon or a glass fiber, and then a structural resin that works together with that to make it both non-conductive and structural at the same time. But what you get is this very clean, very efficient panel edge or panel top. Now you can see at the top here, see the stagger, the face extends up above the insulation extends up above the structural layer. So that allows the design team to really look at how are the different layers of the roof being brought into the top of the wall panels, whether that wall panel slopes or whether that wall panel is the end wall and doesn't have a slope or a rake to it, and where is the structural deck versus the insulation coming across the structural deck, so that we can maintain the continuity of the insulation connection at the roof. Same thing here when we bring another wall panel in next to that wall panel, and we have the exposed edge, and now we're creating maybe a 1/2 inch to a 3/4 inch joint between those wall panels. What do we need to do in that joint? Is there a fire requirement across that between the space from one side of the panel to the other side, in which case we might bring in fire blankets that are also insulating, or we may just blow that joint full of urethane insulation and super insulate the joint. Once the insulation system's in place, you can see here, then we bring in the reinforcement for the structural side, and we top off the panels. So all of this is done really, you could look at it as a 2-day process for the actual casting of the panels, maybe 3 days depending on how complicated the steel is. But the face, architectural face, and the insulation is day 1, structural steel, day 2, and topping off the panel in day 3. And then the panel rests until it's strong enough, and then it's erected. And so here you see some erection photos. Grab a hold of the panel, and it's just stood in place. Until it's braced. Now, once it's braced, then we start to look at the rest of the envelope characteristics. What is taking place with the system? What's been selected for the windows, for the doors? How are they going to be brought together? What's been selected for the treatment between the joints? But the reality is that through these building panels, we're looking at monolithic concrete that from an energy code perspective also meets the air barrier requirements. So I said the building performance, the thermal envelope was the first area that the energy code has greatly impacted. It's now requiring insulation at a higher level in your market than what you've seen before. And in many markets, particularly southern markets, which I represent more of in the United States, insulation where insulation was never required before. And so the thermal envelope is one characteristic that's important, but I think the most important characteristic is that of the air barrier. Because it's really difficult, when you look at the complexity of our building envelopes today, it's really difficult to have high-end architectural aesthetics and a sophisticated continuous air barrier. Now the energy codes, both the NECB and the IECC require, based on ASHRAE 90.1, for all building envelopes to prove a continuous air barrier. And there are two ways of proving a continuous air barrier. Prescriptive, meaning I can once again select from my shopping market the different systems and how they deliver continuous air barriers, or I can prove air barrier performance, build the building, and then do a blower door test on it, which is basically you close up all of the openings except for one, you stick it full of a vent and you measure the suction on the building. And if it meets a certain suction value, then you have a continuous air barrier. But it seems to me awfully complex to wait that long into the process to determine whether my air barrier is effective or not. What happens if I build a stick building with this complicated exterior and we get to day of closing and we get that blower door test going and we find out I don't have a qualified air barrier on that building? Where do I start? Right? So you've delayed the project by weeks to figure out the air barrier. So, depending on the technology you're looking at, just, some of the systems that are out there and how we build, how we lay bricks in with whatever the structural substrate is, or pre-engineered buildings and we insulate or not. This is an insulation, this is not continuous insulation. But more importantly, it's a problematic air barrier constructions. Whereas with tilt-up, we're looking at a monolithic concrete that spans from joint to joint. And in the energy code, it says one of the predefined, I think there are, it's either 20 or 24, there are 24 predefined air barrier constituents or classified air barrier systems. And one of them is cast in place, tilt up, or precast concrete. Because for a span of whatever the space is of the element, it's guaranteed to be a minimum structural thickness and monolithic. And so there is no air penetrating that. There is no moisture penetrating that. And so in this case, you can see here, this is the IECC number, but there's a similar related number in the NECB. But it basically says you have an air permeability of 0.004 cubic feet per minute or per square foot or less, and that is what tilt-up complies with. So we have one very high-performance tilt-up air barrier on this side, and another high-performance tilt-up air barrier on this side, and here's our panel joint. So the energy code also says when you bring two systems together, you've got to maintain the continuity between those systems with an approved air barrier caulking method. As it happens, tilt-up has been under construction since the 40s in modern form. Tilt-up actually got its start at the turn of the 20th century. But in modern form, tilt-up has been building buildings since the 40s and securing the caulking joints between panels with qualified air barrier caulking. And so there's been no change. The energy code had no impact on tilt-up building, whereas every other building system that's out there has been scrambling to configure air barrier development along with thermal behavior. And so this is just a simple backer rod and caulk, Pecora, Sika, you go and find any of the polyurethanes that are out there for your caulking system on the inside, and then it's also recommended on the inside. This is the exterior side. It's also recommended on the inside because it creates the cleanliness of the joint, or it secures the joint for secondary protection and protects the insulation if we choose to insulate within that joint. Either way, we have a qualified air barrier now that is secured, and nothing has changed. We have not changed the way the builders, tilt-up contractors build buildings because of this energy code requirement. So then let's look at the glazing system, because that's important, right? So we now have to have an approved, and every glazing system manufacturer has to prove that they meet both the thermal performance criteria and the air barrier criteria for their glazing system, which means not only do they have to have jam technology that can meet the minimum performance of the glazing system for thermal performance, but they also have to protect for airflow within their system, which means then where that window aperture connects with the tilt-up panel, we have to provide, the contractor has to provide the transitional protection to maintain that air barrier. And so this is how today's tilt-up contractors are fitting these systems in. Again, the insulation coming to the jamb. If you need structural connection, that is integrated into the system, but you'll see that the insulation is continuous all the way out to the window jamb, so that whatever the transition that takes place between panel and window is according to their prescriptive criteria, and then they're caulked. And the simple caulking that's been used always, the methods that tilt-up contractors have always used to caulk to windows, still creates the qualified air barrier that they're being asked for. So really nothing has changed, except for the fact that when you're tasked with creating an envelope solution that meets the thermal requirements and the air barrier requirements, you can be complex and really challenged to deliver the aesthetics with a system that can be upgraded to meet those, or you can recognize that those aesthetics can also come from tilt-up technology and move right through the project design, which is why I showed you some of those earlier projects. Okay, so let's take a look at the roof, and I had mentioned this previous to you when we saw the offset between the face, the insulation, and the structural. So this is just a quick view of ways that this has been happening again for years. I've built a lot of freezers even, -40 blast freezers. With this type of a technology, we have added an integral vapor barrier because of the extreme pressures in projects like that, and so the vapor barrier can be added very easily between the insulation and the fascia width. But otherwise, you have the structural of the envelope, the interior structure here, the interior structure for the roof, deck technology and insulation above the deck, and then vapor membrane, the roof membrane above the insulation. That same thing happens with a tilt-up panel. We just continue it down the side of the building. Structure on the inside, insulation on the outside of the structure, and the fascia width, the insulation, and if I need it, an integral vapor barrier maintains the vapor membrane from the roof down on the outside of the building. And so all of the components of the system are maintained where it is logical, where it needs to be, because really what I want is to solve the energy codes in a very simple way. I don't want to spend any time on solving the energy codes. I want to know that the systems are in place as they're required to be in their minimum state, or be able to take advantage of them and maximize their performance to allow me to do things with the rest of the building. And so there you see the maintenance of the membranes, the air barrier, continuous air barrier, and water barrier through the panel, and all of that is outside of the insulation and the structure. So that sounds pretty good, but is it true? And one of the things that I'm very glad that's taken place is the U.S. Army Corps of Engineers did a study of every structure that they have. Once this air barrier requirement came into being, they wanted to look at, so now they knew they were going to have to build to meet the new energy code, because they're a government entity, and so the government was going to require all of their new structures to meet the current energy code, regardless of its state of location. And so they did an inventory of all their existing structures, all their building types, and did blower-door tests on every single one of them. And what they determined was that not only were they measuring to see if they could meet this 0.04 cubic feet per square foot, but they found that the tilt-up buildings were on average 4 times tighter than any other building that they had in place, and the tilt-up buildings were 10 times greater in air tightness than what their minimum requirements were, the 0.04. And so they had a whole fleet, a whole inventory of tilt-up structures that were already excelling, and they had built those over a period of 30 years. So what do you think the U.S. Army Corps of Engineers is selecting for their new structures? Probably tilt-up. Now, not all of them. They're going to find ways to build other systems. The government always finds a way to give monies to everybody. But the predominant number, and that's why one of the programs we have with the U.S. Army Corps of Engineers right now is understanding the blast performance of tilt-up systems, because a lot of government buildings have new levels of defense protection to them. And so in addition to thermal performance and air barrier, we also are then looking at existing performance. Do you have to upgrade it in order to meet the levels of defense? So with the opaque building envelope, your three options again are to comply with the material properties, comply with assembly rated. In other words, if you have materials that you can pull together, you still have to prove that the assembly, the sum of the parts, is greater than the whole, if you will, or you can demonstrate through a whole test. The third one that we mentioned was the maximum fenestration area. Now this is if there's a problematic one, it's this one, because nobody wants to live in a gray box. No office client is ever going to want to have this room as their office. We want to engage with the exterior. In fact, sustainability says that a certain amount of daylight is imperative to meet sustainability criteria. But the Energy Code realizes that you can only insulate a building so much, and glazing technology cannot meet it. And so the more insulation you put in the opaque wall doesn't do anything, because you've got so much characteristic loss through the glazings. And so the new energy codes, both the IECC and the NECB, control the amount of glazing. It says that basically your glazing cannot exceed 30% of the gross area unless you use automated daylight controls, or unless the 50% of the space is within the daylight zone, and there's a couple other criterias. And then you can increase it to 40%. But I've already showed you some buildings that exceed 40% of gross exterior surface area in glazing. And so there is going to be a change to the way that we design buildings that has nothing to do with tilt-up buildings. It has nothing to do with any system that you choose, other than it's going to lower the amount of glass that exists in buildings. And so I continue to be curious to see what happens with this, but as I said before, the nice thing is that I've already shown you tilt-up buildings that are 60% glass, or maybe 70% glass, and so it can be done if there's a building performance model that allows you to do it. This is why the energy codes are so emphatic about controlling glazing. And that is, so you see here, the blue line is the 1997 MNECB, and that code did not have a constraint on the amount of fenestration, gross area fenestration, that you were allowed. And so as you can see, the fenestration percentage, as it increases, the amount of energy loss, or the energy use per structure, increases greatly. This is the newest requirement right here, and they're maximizing the amount of glass that can be used. And so their energy consumption has flatlined, and they're saying that no more are we allowing energy to be used more dramatically because we're increasing the amount of fenestration. So but there are also opportunities that tilt-up provides that can create this balance between sophisticated daylighting, desired vision, and aesthetic glass. And so you'll see a lot of tilt-up buildings will show you spandrel conditions. This is a tilt-up building. This tilt-up building will also meet the glazing requirements of a 30% maximum glazing area, because a lot of the glass that you see is spandrel glass. Can you see the tilt-up panels in here? So this roof is structurally held by tilt-up panels that exist on the inside. You've got spandrel glass here at the corners that allow the aesthetic of that glass to exist, still allow vision glass in the corner conference rooms, allow punched openings with broad expanses of glazing that can still stay within the 30%, and the structure required to extend on the inner wall up to carry the roof. There's more. Again, a tilt-up structure that is balanced between vision glass, daylighting glass, and spandrel glass so that it can carry the structural loads of the project as well as providing the glazing that's needed. And here's one that integrates the thin brick. Maybe this was in a regional location that required all of their envelopes to have brick integrated with them. South Carolina is a state that's popular for that. But in addition, this is Pennsylvania though, I can see that. But in addition, these are tilt-up panels through the height of that structure that are allowing punched openings and then, if necessary, glazing to exist. Here are some other ideas. So this is part of that dialogue is tilt-up the right solution? Is tilt-up capable of combining high-end aesthetics with superior energy code compliant envelope technology to create that, to engage that future for our building systems? And so you see some curved panels here on this project, angular panels, a lot of opaque wall on that project, but the angularity of the panels is important, and how this panel that transitions from interior exposure to exterior exposure, and look how thick that panel is. How can that be accomplished and maintain the thermal barrier? Panels with very large openings. Now this one's another one that it would be challenged to meet that 30% or 40% if maximized of the new energy code. This is a brand new construction down in Houston, but the tilt-up panels that extend through the height of that, as we begin to apply, I can tell you where this project was constructed, they don't have the new energy code adopted, or this wouldn't have been done. But where these floor plates exist now can become structure, can be expanded, can be spandrel glass, and we can achieve the same look and maintain the performance. Look at the variety of the openings in that. When we think about continuity of structure, when we apply load to a panel, whether it's at the roof or intermediate floors, and we're trying to carry that load down to the footing of the structural envelope, because there is no other structural frame. The panel is the structural frame for the perimeter. You can see that the creativity of the engineer comes into play here as they're able to transfer those loads, both in terms of dead load vertical, as well as the live loads of shear and seismic that are induced into those panels. Or here's some tilt-up that's fitting into a lifestyle mall, a smaller, more personal scale character to the project. Theaters. Here's a distribution center, so this would kind of be a part of that box culture or that box mentality, but I think still is bridging or crossing over into that architectural solution as we begin to embrace higher level thinking in terms of systems that are brought into it, as well as how do we characterize the panels themselves, and challenging contractors to integrate. Look at the way that the panel joints and reveal lines are really have a sophisticated integration with the glazing systems, both in terms of color and line. There's a museum, done all in tilt-up. Obviously all of these are going to be tilt-up, but even schools, right? So school development is one of the classic areas for tilt-up construction. In the United States, it's embattled by the resistance that wants to hold on to the way that we build with masonry, because we want schools to look like they're built with masonry. Now, I can't figure out why that is, because masonry systems, now with the energy codes, five to kick out or 5 to end? 5 minutes. Good. All right. She's going to bring in a shepherd hook and pull me out of here. But in this case, the tilt-up panel is able to deliver that character. I've proven that in a couple of slides, and I've given you evidence of that in a couple of slides. So what does that do to the future of school construction when now you have monolithic tilt-up panel on the inside, so it's durability, it's security, it's maintenance-free interior for the school, which, I've got school-age kids and I know what they're capable of doing, and so that's a great environment for them. But now it has the superior insulation that concrete panel technology can give, and it integrates the sophisticated higher-end aesthetics that we are now characterizing schools with. I think school architecture is one of the most explosive areas in our building culture, and I greatly see the challenge that architects are applying to the project. Here's some Canadian schools. This one's being finished up right now, up in Ottawa, and look at the insulation on that. The insulation is boldly exposed and expressed on the exterior perimeters of those panels, knowing that the continuity of that insulated envelope is being given to the school. Communication structures, look at the big curved panels for tilt up there. And again, curved panels is not going to deteriorate or complicate the solution from an energy perspective or an air barrier perspective. It's maintained through that process. And homes, we were talking earlier before the presentation got started about the impact to housing. Now, this is a smaller scale, and so there's a scope, a mobilization difference that happens when you're thinking office buildings and schools and warehouses versus single-family residences. But to tilt up, it doesn't matter. It's really only to us as delivery companies and how we think about the projects themselves that challenge us. We have the ability to cast these panels in areas that are in concert with the footprint of the building, not necessarily on the footprint of the building. And this is, I always like to show the extravagant. I like to take you well out of your comfort zone. And if each one of us had an opportunity to do a project like this, none of us would have any hair, but we would all be appreciative of the tilt-up solution. This is a Swedish architect that designed this casino, but didn't design the construction system, just designed the architecture and said, now go build it. And it happens to be in South Africa, and they didn't know how to build it. They could not figure out how to build these panels, or these buildings, let's just say buildings. They couldn't do it out of masonry, they couldn't figure out how to do it out of cast in place, because these panels are curved, and they taper, and then they just do all of that. And so a contractor said, hey, I think I can do that on the ground in tilt-up and stand those up. And they did that. So I'm right on time with my 5 minutes. I want to finish up with what questions. What questions do you have? What brought you to here that you were hoping to hear that maybe I didn't answer, or you want to press me a little further on? The two characteristics of tilt-up construction that I apply to every project are that affect its economy of scale are the casting area for panels and the cost of the crane, right? Because you're going to stand large panels or panels. It doesn't have to be large. On a house, they wouldn't be large. But you have to stand the panels up, or you have to move them from casting location to permanent location. And so applying the economy of scale, if you take a tilt-up contractor from Vancouver, in Vancouver there's an awful lot of tilt-up. I don't think there's any residential tilt-up that I know of. That just may not have been reported to me. But most of the Vancouver tilt-up is really industrial, manufacturing, market-driven. And you take a contractor that has that model built, and they understand how to cast panels on the large floor slabs of an industrial building and walk a crane around the perimeter and stand them up. That's very different from the intimate side of a house where you might have to cast panels 150 feet away on a driveway and then pick that panel up and move it. That doesn't mean that it can't be cost effective, because I can still build that house faster than I can frame it. It just means that I have to account for that in the way that those panels are designed. Now, for some it doesn't matter, because you can't achieve the aesthetic in a wood frame house for that modern concrete that you can out of tilt-up, so that plays into it. But to me, if you can investigate right away the impact of casting location, which can be stack cast. You know, I could have a driveway sitting right next to the house foundation, and I could stack cast all my panels for the house right there. We were talking before the presentation about San Diego Children's Museum, a rather large museum in an urban infill setting. They brought a 500-ton crawler from the docks of San Francisco and shipped it down to San Diego, set it up, and it erected all of the panels with the crane sitting in one location. It just swung a big boom out and set all those panels. So that could be done. Or sitting in that area, stack cast right adjacent to the house foundation, pick one up after another and set it in place.
That 3A time frame
Yeah.
For stacking?
Yeah, if you're stacking, yeah, because really, in order to start the next panel on top, you have to have a day of cure on that top panel. Yep. And that's if you cast directly on the back of the tilt-up panel. I've also seen companies use an alternative form of stack casting where they don't rely on the face of the panel below it for the face on top, but that's because of the odd size of the panels. Excellent question. What else? Doggone it, I did it. I answered all the questions in my presentation. Well, okay, so some of the things I want you to take away. Where do you go from here, right? That's the question that all of us, whenever you sit in on a presentation, there's way more information thrown at you than you can absorb and put in place. And so real quickly, you want to do an inventory of what you learned today. What are the top 3 things that you learned today that either challenge you, excite you, or drive you to do something more? To do the same thing you're doing, or to know, at least know, that there are resources available for you. What experiences do you have with the energy code that may have brought you here? Maybe you were looking for something that was more simplified, or maybe more consistent in the way that it delivered a solution. That's one thing that you might ask yourself. And really, ultimately, do you think the tilt wall has the power, has the potential to change your idea of what the built environment can be? Because the one hesitation that we still have in any industry, doesn't matter whether it's a precast industry, cast in place industry, tilt up, the concrete industry, the main stipulation that we have is that not everybody in the world is like me and lives and eats and breathes concrete, that has concrete in their blood. And so me, I like concrete for the sake of being concrete. But you guys all have clients, and maybe you're a client of yourself, where I don't want necessarily concrete. But can I adapt the vision I have for this project to integrate systems because tilt up, tilt wall has matured to the point where it can bring together modern aesthetics from different cultures and deliver the solution for the building, but capitalize on the fact that it is such a sophisticated energy envelope that I can remove that from the equation. I no longer have to worry about that component. It's delivered automatically in the inherent technology of the building. Where can you turn for more information? Here's my email address. It's the back half of my email is our website also. You've got you've got local expertise in Tilt Wall, Ontario, and Dayton Superior has representation up here, and architects, Barry Bryan Associates. I mean, you have incredible experience in your marketplace. Really, it's just about reaching out and making it effective for you. So I appreciate your time today. Last question, one more chance for last questions? Yes, sir.
These very, very tall panels, all the weight is borne on the foundation wall, or do they pick up on slab edges as they go up?
No, so in all those tall walls, well, not all of them, but the majority of tall panels, so the 6-story office building, let's look at that. Let's not look at the 22-story project I mentioned earlier. Those were cladding panels. It was a site cast, precast methodology. But the tall walls carry the floor plate loads at the edges. So you'll have interior columns, so they'll carry the tributary load out on that perimeter, but carry that all the way to the foundation, which is a challenge. We didn't get into construction technology, but that is a challenge for the foundation systems. But I will tell you that tilt-up systems, foundation systems, are also simplified. Thank you. You guys are a great presentation audience. Appreciate it.